So the last video, we modeled the caustic curve from a parabola as a Bezier, a cubic Bezier inside a Inscribed Equilateral Triangle. This time I'm going to do a model. In that case, the two equilateral triangles, one containing the parabola and one containing the caustic, one was the medial triangle of the other. In other words, it was the triangle that joined up the center points of the three sides of the outer equilateral triangle. In this case, I'm going to generalize that so that instead of the midpoints were going to be a general distance down some particular proportion equal on each side. And this gives us a model which pertains to the situation where the light is coming in obliquely, not horizontally, to reflect in our parabola. So we're going to start the model with our equilateral triangle ABC. Now it's critical when we're doing these things that we go either clockwise or counterclockwise for both triangles. So I'm going that direction. I need to make sure I do the same for the other triangle. The reason is that our parameter location T is going to be used heavily, and that goes from start to finish. So anyway, here's my second triangle. Neither of them look equilateral yet, but hold on a second and we'll get them equilateral. There's a length A. Then we're going to make this one length A, and we're going to make this length A. Okay, so the outer one is equilateral. The inner one is going to become equilateral once we start specifying parametric distance. Here we'll call that S. So the parametric distance being proportion. It's a proportion S along that line segment. This one's proportion S along this line segment. And this one's proportion S along this line segment. Okay, so there's our inner triangle, there's our outer triangle. Well, let's line up that inner triangle this way. That's the one that contains a parabola. It'd be nice to have that kind of vertical. I'm now going to draw the line here, which is tangential to the parabola. This smaller triangle is going to define the control points of the quadratic Bezier, which is the parabola. We're going to make that proportion T along there. This one proportion T along here. Okay, so this defines the parabola. We can watch it if we like. And move this T, and there's a piece of parabola there. But I don't really want that to be present, so let's get rid of it. What I want to do is turn this one purple because I'm going to focus on it. It's going to be an important line. And then I want to sort of hide these guys because they're going to get in the way. I'm going to put a bunch more lines into this diagram. I don't want the clutter to get in the way. And then I'll also remove these S's. Not removing them, I'll leave them in place, so I just hide them. Okay, so this is the tangent to my parabola. Now I'm going to draw the lines that start to define our cubic Bezier. So these first two lines, this one is proportion T along here. This one is proportion T along here. And I want you to notice, look, G looks like it sits on that line. Let's just verify that. We can do that by asking for the symbolic distance between G and IJ. and we get that symbolically 0. That means it does lie on it. It's not an accident. H, I suspect, is going to lie on the other one once we make this T. And it certainly looks like it. The other question is, how far along is G? Certainly not halfway, but let's just have a look at distance IG. Okay, and then let's look at distance IJ. That's the complete length of that line. Well, it's almost the same, but you see that IG is S times that. So this is proportion S along this line, which is the same proportion as D is along this line. So I'm now going to draw the final line that's going to construct my cubic spline. This line is going to be tangential to the cubic spline. L needs to be proportion T along that line, and M needs to be proportion T along this line. And so what do I want to show? I want to show, first of all, that the intersection here is proportion T along GH, because that intersection point, LM here is the tangent to the Bezier spline, the cubic Bezier. This is the tangent to the quadratic Bezier, to the parabola. And the tangent point on the parabola is proportion T along GH. And so is this the tangent point, the intersection between these two? Let's just see. There's the line N, and we want to know distance GN over distance GH. And that is T. So that says that that point N is in fact the tangent point. So, and then this is the line which is tangential to the cubic spline. So it would be the reflection of some line coming in, of some ray coming in here and reflecting up there. So let me get the incident ray by reflecting that one back in the purple line. Now here we go. There's the reflection, OP. Now that is the incident ray that is going to cause the cubic spline to be the end lobe of its reflections. Now the question is, are these coming in parallel, or are they coming from somewhere else? And so we need to look at the angle between OP and the baseline there, BC. Now, that's not particularly simple. We can look at it, but what is important is what it does not contain. It contains S, the distance of D, E, and F along these lines, but it does not contain T. Hence, it's going to be constant all the way around, and hence these rays are going to be parallel. We can exhibit that more easily by drawing longer rays through here. And we can move T and just watch. These certainly look like they're moving parallel. So what this is showing is that the curve formed by this line. Okay, I need to make sure I've got the right thing selected. The curve formed by this line. This is the cubic spline. Is the caustic of a set of rays coming in this direction.